Good evening, everyone. Welcome you all to this NPTEL course named as a study guide in organic retrosynthesis problem solving approach. So, the course instructor for this course is Professor Samik Nanda from IIT Kharagpur, and I am Anirban Maiti from IIT Bombay, one of the TA for this NPTEL course. So, this is the week 8 NPTEL tutorial. So these synthons and synthetic equivalents are known in retrosynthetic analysis. So already we have discussed about synthons and synthetic equivalents. So from where we can get synthons and what are the synthetic equivalent of the corresponding synthons. Okay, so yeah. So basically synthons, if we do heterolytic cleavage, that time we can s- we can get two synthons. One is donor synthon, another is acceptor synthon, right? So donor synthon basically it will abstract the two electrons from this bond, CC bond, and so automatically this carbon will show positive charge, right? So this minus, so that means it can donate electrons, so it's called donor syntone. And this is, so this carbon can accept the electrons, so it is called acceptor syntones. So accordingly we can get the corresponding synthetic equivalent. So right, in chemical reaction, in forward synthesis we can't use this minus and plus charges, right? So we need some neutral molecules, and in situ we can generate this donor syntone and acceptor syntone. So this donor syntone and acceptor syntone to get, so from where we can get. So basically we need to talk about synthetic equivalents. So already we have discussed about these donor syntones, and like R minus, if it is R minus mean alkyl anion minus alkyl anion, then what will be the synthetic equivalent? Synthetic equivalent would be the Rx, and generally in Rx, R is delta positive, X is delta negative. So we need R minus. So we need to convert this Rx to organometallic reagents, right? So basically we can insert any metal between this Rx bond, and we can generate the R negative or alkyl anion intermediate. So what will be the corresponding synthetic, like what will be the reasons for this synthetic donor symptoms? So RMGX or RLI, where this R is delta negative, right? So cyanide ion, similarly cyanide ion, so the corresponding synthetic equivalent is HCN. And in HCN, and what will be the derived reagent NHCN, where Na is Na plus and Cn minus. So this is ionic, right? So Na plus and Cn minus. So ionic compound. So from here you can easily get the Cn minus cyanide ion. What about the acetylide? Acetylide, if you see, so this is C triple one C minus, and it is having this R triple one CH. So this is the synthetic equivalent. That means if we generate the minus as here, so from how you can get, so if you treat this acetylene like this alkyne, terminal alkyne with n-butyl lithium base, okay, suppose if we treat this alkyne with n-butyl lithium, right, then this n-butyl minus Li plus, so this n-butyl minus, so this base will abstract this acetylene proton, and it will give this R triple one C minus and Li plus. Okay, so this acetylide anion you can easily get. Right? What about enolate? So enolate, that means if we treat any carbonyl compounds, so this carbonyl compounds, if we treat with similarly with suppose LDA, lithium diisopropylamide, that time we can easily abstract proton alpha to the carbonyl compound, and we can easily generate this enolate, right? What about elide? Elide is it is well known for Wittig reaction, Betic reaction, and from where we can get this halide. So basically, if we have this halide type of compound, and if we treat this halide with PPH3, so PPH3 will undergo SN2 reaction, and it will generate this halide. Sorry, it will generate this salt. So this is the salt, right? And if you treat this salt with base, so base will abstract this proton, and it will give corresponding carbanion, and that will be the corresponding halide, right? And this alpha nitroanion is, you can easily take proton from alpha to this nit, so this proton, and you will easily generate the alpha nitroanion. Just a minute. So similarly, this acceptor synthons also you can easily generate from the corresponding synthetic equivalents, right? So like alkyl cation we can get from this R halide, where this R is delta positive, and so that means you can easily generate the alkyl cation, right? So there are others, acylium ion. So this positive charge beta to this carbonyl compound, from alpha beta unsaturated carbonyl compound we can get. So alpha to positive charge we can get from alpha haloketone, and this beta positive charge with respect to this alcohol, so we can easily generate from this uh, epoxide. Okay. So yeah, so coming to the next problem for this today's class. So this is the compound where you can see, so this is the molecule, six member molecule. Yeah, six member ring, where you can see the stereochemistry between two ester is trans, and stereochemistry between this methyl and hydrogen is cis, sorry, trans. So if you see the retrosynthetic analysis for this molecule, so if you see, so this is the six member ring, typical six member ring. From where we can get this six member ring? So we can get from the, if you think, if you have the six member ring, and if we are doing retrosynthesis, so you can easily plan about Diels-Cellar reaction or 4 plus 2 cycloaddition reaction to get this six member ring, right? So the six member ring, so basically in six Diels-Cellar reaction you will get cyclohexene, right? So Diels-Cellar reaction between diene, sorry, diene and dienophile, so you will get cyclohexene. S- and if you reduce the cyclohexene you will get the corresponding cyclohexane, right? Cyclohexane reduction if you do. So now if you see this, your target molecule, so it is normal cyclohexane. That means if we think about reduction step, so reduction, so this functional group interconversion, that is the reduction. Okay, so reduction of double bond, you can easily think about this molecule. Okay, so just if you do reduction of this double bond, you can easily get your target molecule. Now how you can get this cyclohexane? Now it is cyclohexane, right? Cyclohexane, as we talk about Diels-Cellar reaction, so we can easily get a 4 plus 2 cycloaddition reaction to get the cyclohexane. Now if you see the stereochemistry between two ester, so this ester should come from dienophile, right? Because dienophile need to be electron electronically deficient. Okay, so dienophile so should contain this ester, and ester are electron withdrawing group, so both ester should come from the dienophile. Now if you see the stereochemistry in cyclohexene, these esters are trans. Okay, trans in geometry, so you need trans So in dienophile, this ester should be in trans, okay, and this is your cyclo on butadiene, right? So now I will show you how the stereochemistry comes. Okay, so in Diels-Cellar reaction, so suppose yeah, in Diels-Cellar reactions, this diene or two approaches there. If you thinking about stereochemistry, so two approach you can think about. Like, so first this diene you can make, like diene is in plane. So keeping diene in plane, suppose this is the diene. So diene is in plane. Okay, now so now this dienophile, so dienophile can approach from bottom phase or top phase. Okay, so if it is approaching from bottom phase, what will be the scenario? Okay, so suppose yeah, this will be the H, this will be the ester CO2R, and this will be the methyl, and this will be the ester. So here we are thinking that diene is in plane and dienophile is approaching from bottom phase. So what will be the transition state? So this CC bond will form this, and this CC bond will form, right? So if you see, so this is in bottom phase, okay, or down to the diene. Okay, so what will happen if and after the Diels-Cellar reaction, what will happen? So these two groups, okay, so these two groups will go up, okay, after the Diels-Cellar reaction. Okay, so these two group will go up, and this hydrogen will come down, and this ester also go down. Okay, so the movement, the direction of ester, this ester and this hydrogen will be the towards down, and this ester and this me, it will be towards top page. Okay, so if you see this bottom page approach, so you can easily get this cyclohexene with desired stereochemistry. So this will be the cyclohexene, and as I told you, this ester and this hydrogen, so both are beta. Okay, sorry, alpha. So first we'll draw the alpha CO2R, CO2R, and this hydrogen. Yeah, alpha, and this Me and CO2R, these are beta. Okay, so this is the Me. Sorry. So the stereochemistry you can see. So basically this methyl and this ester will be cis, and this ester and this hydrogen is cis. Okay, so you can easily get. Okay, so this is the bottom phase approach, And if you think about top phase approach, that time you will get the opposite stereochemistry. Okay, so in this reaction basically you will get both stereoisomer. Okay, and that will so both 50-50 you will get 50-50% mixture. So basically that will be the racemic. Okay, so both racemic compound you will get. So what will be the other product? So if dienophile is approaching from top phase, so from top phase, that time you will get completely opposite isomer. Okay, so like this ester and this hydrogen will be it will be beta, and this amine and this ester will be alpha. Okay, so both approach will happen because we are not controlling the stereochemistry here. So both dienophile will come from both top phase and bottom phase, so you will get mixture of 50-50 mixture of both stereoisomer. So basically you will get racemic. Okay, so this is the example. Okay, so this retrosynthetic analysis is done for this molecule. Now coming to another Diel cellular based approach, where you can see, so this is the molecule. Okay, so this molecule, if you see, so this molecule is a bicyclic system, and this is also a fuse ring, 5 member ring. Oh, and this is, so this is two bicyclic system with 5 member fuse, 5 member ring. Okay, and if you see this carbonyl group is there, acetate, methyl, and this olefin, cyclohexene is already there. So Diel cellular reaction here also we can think about. Okay, so basically if you see the retrosynthetic analysis, what we can think. Okay, yeah. So basically, Diel cellular reaction, if this molecule we are planning, so Diel cellular reaction we can plan. Diel cellular reaction mean, so this CC bond and this CC bond. Okay, so this CC bond if we break, what will happen? So basically, via Diel cellular reaction, like via Diel cellular reaction, this CC and this CC mean this 6 member ring we can think about. Okay, and intramolecular Diel cellular reaction is happening, that's why we are getting another fuse ring. So that is not a problem. Now we have to think about this Diel cellular reaction. Okay, so this CC bond and this CC bond we are forming in Diel cellular reaction. So what will be the starting material? So this will be the starting material. Okay, so yeah, and from I will discuss how this Diel cellular reaction is happening and how this complexity of this molecule we are getting via DSLR reaction. Okay, and this molecule, if you see, this is an cyclic butadiene system, and having this carbonyl chain and acetate and this olefin side chain. So basically, if we do some de-aromatization of this aromatic ring, so we can get this reaction. Okay, so this is the functional group interconversion. Now in forward synthesis we need to start from this starting material, this alcohol. So this alcohol if we treat with lead tetraacetate. Okay, so what will happen, this oxygen of alcohol will coordinate to this lead tetraacetate, and one of the acetate from this lead will will add to this center. Okay, so that is, and we can get this diene, cyclic diene. Okay, so this, and if you carry out this dual cellular reaction, we will get this product. Okay, so this complex molecular structure. So how this dual cellular reaction is happening? So basically this molecule if we redraw like yeah, so we can draw like, yeah, so we can draw like this. This is the, sorry, just a minute. So this is the methyl, and this is the double one. Okay, and this, if you see the stereochemistry, that is trans. The stereochemistry of this olefin, this is trans. Okay, and I can draw properly. Yeah. So this is a trans olefin, and on acid, this acetate also remaining. So this molecule we can redraw like this. Okay, so now this conformation is yeah, this double bonds also remaining. Right, so now this, it is, now this is complete drawing. So this is the acetate, so this carbon, so first, if we can think this carbonyl group, so carbonyl group, then this olefin, then another olefin, then this carbon containing acetate, and this one two three one two three four five member ring, five member change, 1 2 3 4 5. Okay, so now this cellular reaction will happen between this, like, so what will happen, so suppose this will add to this, so though it's not a chain process, and yeah, and it will add to this. Okay, this will go like this, so you will get this molecular complexity structure. Okay, so like this we can, like applying this dual cell reaction, we can get some complex molecular scaffold. Okay, so this is the benefits of dual cell reaction, where you can generate molecular complexity in your desired molecule. Okay, so coming to the next example. Yeah, so the next example, so this molecule is tarpinol. Okay, so tarpinol, again, so we can plan about some 4 plus 2 cycloaddition reaction to get this molecule. So if you see, this is having this cyclohexene already in this molecule. Okay, so cyclohexene is there, that means this reaction we can easily plan. So we can think about this cc bond disconnection, and we can think about this diene, so this diene, and this side dienophile, right? So this diene and and this is dienophile. Okay, so now in forward synthesis, so this dienophile, from where we can get, so dienophile we can easily get, if you see, this is having this tertiary alcohol. Okay, so if we are having this ester, and if we add two equivalent of this Grignard reagent, two equivalent of methyl magnesium bromide, we can easily get addition of two methyl group to leads to this tertiary alcohol, and this methyl magnesium bromide we can easily get from methyl bromide from by treating with magnesium zero, okay, or magnesium turnings. So now, so if you see this forward this retrosynthesis, so in forward synthesis there will be one problem. What is that problem? Problem is this in Diel-Cell reaction. In this Diel-Cell reaction, if you see this diene is okay, but dienophile. What about dienophile? Dienophile should be electron deficient. Okay, electronically poor. It should be electron Califor, right? So this rhinophile now it is not having any electron withdrawing group. Okay, so this real cellular reaction is not that much efficient. So instead of having this tertiary alcohol in dienophile, we can think about this as a dienophile. Okay, so this dienophile and this diene. Okay, so this real cellular reaction between these two we can plan. Okay, so and that will be the efficient. Okay, later we can convert this ester to this tertiary alcohol. Okay, so like that we can think about this functional group interconversion of this tertiary alcohol to get the ester, while we are adding this methyl magnesium bromide in last stage, and this is a reaction we are getting from this 9 and then the dienophile. Okay, so you got it. So I guess, yeah. Yeah, so this in this plan, so first we are thinking about this functional group interconversion to get this tertiary alcohol from this ester by adding two equivalent of methyl magnesium, methyl grignard or methyl grignard, and we can get this tertiary alcohol, and the cyclohexene, as we talk already, that we can get from this via this cellular reaction between this diene and this methyl acrylate dienophile. Okay, so in forward synthesis, so first what will happen, so this Diel-Cell reaction in heating condition, normal heating condition, we will get this cyclohexene. Yeah, so in forward synthesis, what will happen? So in this first step, so first Diel solar reaction between this diene, so this is the diene butadiene, and this is the methyl acrylate dienophile. So what will happen in if you heat this reaction mixture, like normal heating 100 degree or 150-degree, you will get easily this cyclohexene via Diel-Cell reaction. So the cyclohexene, now we need to convert this ester to get this corresponding tertiary alcohol. So basically, if we add this methyl magnesium bromide or methyl magnesium iodide as a Grignard reagent, so this will add to this ester. Okay, so ester mean it will add we can add maximum two equivalent of this Grignard reagent, and we can easily get the addition of two methyl groups along with this tertiary alcohol. Okay, and this leads to your desired target molecule. So what it is having, so it is a 6 6 fuse ring, and the left hand side it is having the alpha beta unsaturated ketone. Okay, and you have another ester in ring junction, right? So this is a fuse 6 6 fuse ring, and you are having the alpha beta unsaturation uh, with respect to this ketone. So how you can synthesize, how you can plan to synthesize this molecule? Okay, so then plan mean retrosynthetic study we have to do. So how you can, so first retrosynthetic plan is that function like this. Okay, so this bond, just a minute, so I'll, yeah. Yeah. So first this CC1 disconnection approach. Okay. So this CC1 disconnection approach, if we think, then what will be the possibility? Okay. So this is alpha beta unsaturated carbonyl compound, right? So we can think about aldol reaction. Okay, aldol reaction followed by dehydration. Okay, if we think about aldol reaction, then what will happen? So we can think about this beta hydroxy alpha beta, so it is unsaturation. Now we can think this beta alcohol here. Okay, this beta alcohol here. So if you do dehydration step, then you will get this alpha beta unsaturated compound. So basically you have to do a aldol reaction, you have to carry out an aldol reaction. So aldol reaction mean you can have these two carbonyl compounds. So this is COCH3 this side, and this is another carbonyl compound. Okay, so basically base will abstract proton from this side, and then normal aldol condensation to get this corresponding beta hydroxy alcohol, then dehydration, you can get this compound, right? So the next disconnection approach, what could be? So we can think about, so this CC1 disconnection. Okay, this CC1 disconnection. So if this CC1 disconnection we are just a minute. Yeah, my slides are visible, right? Okay. Yeah. So so the next is this CC1 disconnection we are thinking. Okay, so this CC1 mean what will be the corresponding synthons for this CC1 disconnection. So we can think about positive charge here and negative charge at this carbon. Okay, so now negative charge this carbon means, so this is a active methylene compound. Okay, so if you see, so this is the active methylene compound, it is having highly acidic this CH proton. Okay, now if you take this proton by treating with any base. Okay, any base, and then if we do Michael addition to this, so this is methyl vinyl ketone. Okay, so the commercial name is MVK, vinyl ketone. Okay, so if we think about the this is 1,4 addition mean, yeah, 1, 2, 3, 4, yeah, 1,4 addition or Michael addition. So so nucleophile is nucleophile we can generate from this active methylene compound. So first step is basically Michael addition, and second step is basically aldol reaction. Okay, so you can get easily this 6 fuse this alpha beta unsaturated compound. Okay, so so basically, so the this is aldol reaction, aldol condensation. Okay, more, it is more correct, aldol condensation, and this is Michael addition. The next disconnection approach is based on Michael addition. Right. So now we will. So this is the retrosynthetic analysis. So now we will see the corresponding forward synthesis for this molecule. Right. So forward synthesis. So we have to take this active methylene compound and methyl vinyl ketone, and we have to treat this compound with base. Okay. So base. This is the base, sodium ethoxide or ethanol. So in ethanol, so we can take. Okay. Mm, so then, so basically this base will abstract this proton. So this is the active more acidic proton. Okay, so base will abstract this proton. So now this carbanion will generate here. So this carbanion will attack to the corresponding methyl vinyl ketone. So this is having this alpha beta unsaturation. Okay, so this is the electrophilic site, more electrophilic site, delta positive. So this carbonyl will attack to this MVK as a 1,4 fashion, and you will get the corresponding this is the allol Michael Addison product, right? Michael Addison product. The next step is we have to carry out, so in same reaction condition, basically the reaction condition is same only, okay, but in same reaction condition in one pot, first Michael addition will happen, then in the same reaction condition allol reaction will also happen, okay. So this base is already there in reaction medium, so it will take proton to from this side, okay. So this proton it will take again, and it will undergo this allol condensation reaction, okay. So it will generate this alpha beta, so beta hydroxy carbonyl compound. So now the next step is dehydration reaction, okay. So yeah, next step is dehydration reaction. If you do heat, if you heat this reaction or this reaction medium, so you will get the elimination of water, and you will get the corresponding product, okay, desired product. So now the reaction, so reaction in this reaction, two in one pot two reactions are involved. First is Michael addition, so this first step is Michael addition, and the second step is aldol condensation, okay. So this reaction is discovered by Sir Robert Robinson. So that's Robinson. So that's why we call as Robinson annulation reaction. Okay, annulation mean formation of ring. Okay, if you heard anywhere that annulation happening, okay, annulation mean the formation of many rings. Okay, so you can see here one ring was there previously, and you are creating another ring. Okay, so this ring was previously there, and you are generating another ring. So that's why it's called annulation, and this is called Robinson annulation. Okay, so this Robinson annulation reaction mean Michael reaction followed by aldol condensation. Okay, now if you carefully observe, so in one condition only two reactions are happening, okay. So in this first condition only Michael reaction also followed by aldol condensation, both are happening. So that's why we call this type of reaction, we like it's known as domino reactions or cascade reaction or tandem reactions, okay. So the three names are there, but meanings are similar, okay. So what does these domino reactions mean? So basically domino reaction mean you have to carefully design a multi-step reaction, okay. You have to, for like multi-step reaction uh, is sometimes you have to design a multi-step reaction. How you can design? No, you have to think about one pot sequence, okay. Multi-step reaction in one pot sequence. So how you can design? Like you can design in such a way that the first step of this multi-step reaction will creates the functionality that will trigger the second reaction, okay, and so on, okay. So basically the first reaction here, if you see, the first reaction is generating two carbonyl compounds, okay. So Michael addition is generating two carbonyl compounds, and the reagents are already there in reaction medium. So this Michael addition, after Michael addition reaction, you are having two carbonyl compounds. So in the same reagent condition, aldol product it will happen, okay. So you have to design in such a way that the first step, whatever functionality will generate after the first step, so that will trigger the next reaction, okay. So what is the benefit of this domino or cascade or tandem reactions? So there are many benefits, like it is more economical, okay, and also environmental friendly. Economical, why? Because in same pot, in one pot you are doing two three reactions, multi-step reactions, okay. So that is very interesting. So it is highly economical and also environmental friendly, okay. So this is the, so Robinson annulation is an example of this domino or cascade or tandem reactions, okay. So now you got an idea about this type of reactions. So now So we'll see the next problem for retrosynthesis. Okay, so this is a simple molecule. Okay, so this is cyclohexanone. Okay, so six member cyclic ketone, cyclohexanone. So how you can plan the synthesis for this molecule? How you can think? So basically you can think like so here the functional group is this carbonyl group, right? So this is the functional group CO. So how you can do think of retrosynthetic CC1 disconnection? So you can think about this CC1 disconnection. Okay, so this CC1 disconnection, what will happen? Also this CC1 disconnection. Okay, so both CC1 disconnection mean we were thinking ki this carbon should be a delta positive charge and this carbon should be a delta positive charge, and this carbonyl carbon, so that will be nucleophile, so that can act as a nucleophile. So that means carbonyl compounds you want as a nucleophile mean you have to think about Ompulang chemistry. Okay, so basically Ompulang already we have discussed in last week. Also Professor Saming Nanda many times discussed the Ompulang chemistry in his talks. So Ompulang, how we can generate? Okay, so basically we if we have the 1,3 diethane derivative of this formaldehyde, so we can easily generate ampulang from this compound. Like carbon ion we can easily generate by treating with base, and then if we do, so now we are having this Rx and RCl, Ri and RCl. Okay, so this will act as a electrophile. Okay, so we will generate nucleophile from this compound, and we'll add these electrophiles into the reaction medium, and we can get the corresponding product after nucleophilic substitution reaction. Okay, so this is the retrosynthesis. And how we can generate this 1,3-diethane derivative? So this we can derive from this corresponding formaldehyde compound. Okay, so this is commercially available. So in forward synthesis, so we'll take the formaldehyde, right? So we'll take this formaldehyde, and then we'll, so in order to generate the ampulang derivative, okay, so we have to have that six member ring with this sulfur and sulfur. So how we can get? So if we treat this compound with 1,3 diethane, so this is the 1, 2, 3, so this is the 1,3 diethane. Okay, and if we treat with Lewis acid, so we can easily get the protected aldehyde. So protection of this formaldehyde with 1,3 diethane, we can get this compound. Okay, so now I have mentioned the pK of this compound is 31. pK mean this proton we are thinking about. Okay, so this proton we are thinking about for pK values. Okay, now this pK is 31. So now in order to abstract the proton of this compound, okay, so we need to have a base who is having the pK value more than 31. Okay, so now we can use this n-butyl lithium. N-butyl lithium, this is in uh, alkyl alkyl lithium. Okay, n-butyl. So this is the 1, 2, 3, 4. Yeah. So this is the n-butyl lithium. So the pK of this n-butyl lithium is 50. Okay. So that means it can easily abstract the proton from this 1,3-diethane derivative, right? And if you treat, so first you have to take this 1,3-diethane in your reaction round bottom flask. Okay, then you have to add n-butyl lithium drop wise, and the temperature you have to maintain at minus 78 degree centigrade. Okay, so then, so after complete addition of n-butyl lithium, so you have to wait for at least 30 to 40 minutes, so to generate the carboanion. Okay, so at the center. Okay, and then you have to add this electrophile. So this is the electrophile. So it now if you see carefully, it is having two Rx. Okay, so this C iodine and CCl. So first time, so if you think about the living group aptitude, which is better living group in between iodine and chlorine? So obviously iodine is better living group. Okay, so first, what will happen, the displacement will happen at this carbon. Okay, so and this carbon and this carbon bond will form fast in this condition. Okay, so you will get this compound. So now again another proton is still remaining, right? So this proton we can easily abstract by using again n-butyl lithium. So again we have to add this n-butyl lithium into this compound in THF. THF is a solvent. Okay, so ether, it is tetrahydrofuran. THF, we know, tetrahydrofuran. So if you add n-butyl lithium into this compound, again it will abstract this proton, right? And it will generate this carbanion. Okay, so now the second nucleophilic SN2 reaction will happen. So and you will get the corresponding this compound this pyrocyclic compound. Okay, so this is what, this is actually basically protected form of ketone. Okay, so now you can easily generate the corresponding ketone by deprotection of this 1,3 diethyl derivative. So this deprotection also known, so you can use any Hg2 plus salt, Hg2 salt, and you can easily deprotect this 1,3 diethyl, and you will get the corresponding carbonyl group. So this is our target. This was our target in previous slide, and now you can see how we can easily synthesize this cyclohexanone, this 6 member cyclic ketone from this formaldehyde. Okay, so very interesting. Now, so now what we will do, we'll do some other example, and we'll use the cyclohexanone problem here. So if you see this carbonyl, this compound, it is having dicarbonyl compound. Okay, so this is aldehyde, this is aldehyde, and this is carbonyl. Okay, now how we can plan the retrosynthesis? Okay, so now if we think this molecule, how we can plan, or how we can imagine in our mind, or how you can visualize this molecule. Okay, so this molecule and this molecule are same basically. Okay, so both are same molecule. Okay, now you can easily visualize how this molecule we can uh, like how CC disconnection approach we can think in this molecule. Okay, so now we can think, so this is the carbonyl compound, this is the alpha carbon, and this is the beta carbon. Okay, so this alpha beta to this carbonyl compound, so we can easily plan the red CC bond disconnection for this is this CC bond. Okay, so we can think this carbon can be a positive, and this carbon can be a negative charge. So basically, alpha beta unsaturated compound we can think about, and for this part we can think about Ampulang chemistry. Okay, so this alpha beta unsaturated compound. So this is the synthetic equivalent for acceptor syntone, right? And what will be the synthetic equivalent for this donor syntone? So same nitromethane, already we discussed in last slide, right? So very interesting example. Yeah, so in forward synthesis, so this is the nitromethane we have to take. So now, so nitromethane we are abstracting proton, right? So we will treat this nitromethane with base, and that base will abstract proton. So for this type of reaction we should know the basicity, the pK values for the corresponding acids, and pK value for the corresponding acids of corresponding conjugate acid of bases also. Okay, so this pK value we you should know Otherwise you don't know which base you will use in your reaction. Okay, so this pK value for this nitromethane is around 10. Okay, if it is nitroethane, so for nitromethane it is 10. If it is nitroethane, the pK value is 8.5. So basically you can, so the pK value for nitroethane is 8.5. So you can think the decrease of pK value for nitroethane. So that is quite obvious, because this extra alkyl group methyl have plus I effect, and due to this plus I effect, so the acidity of this carbon will, the proton of at this carbon will get decreased. Okay, so nitroethane pK value is 8.5, so nitromethane pK value is 10. So for to abstract the proton from nitromethane, uh, you have to use the base which is having pK value more than this base. Okay, pK value of base mean we are thinking the pK value of their conjugate acids. Okay, so in general we will see, we will say ki pK value of base. Okay, but that does not make any sense. So pK value of base mean we are telling about the pK value of the corresponding conjugate acids. Okay, so pK value of nitromethane is 10. So we have to use the base which is having the pK value more than 10. Okay, so we can use sodium methoxide. Okay, so that methoxide or ethoxide, that pK value of corresponding conjugate acid is almost 15 or 16, right? So we can use, so this base is sufficient to abstract this proton from nitromethane. Okay, so this nitromethane, and we take sodium methoxide in methanol, we can easily get, yeah, we can easily abstract the proton from here. So we can generate the carboanion. Okay, now if we treat this carboanion with this alpha beta unsaturated compound, so this carboanion will attack to the beta carbon of this unsaturated compound, right? So beta carbon is more electropositive, so we will get the corresponding product, right? So you get the 1,4 addition product or Michael addition product. So this is the Michael addition product. Michael, yeah, Michael addition product or 1,4 addition product. Now the next step is basically you have to do the NAF reaction. Okay, NAF reaction already we have told about, do we have discussed. If we treat with titanium trichloride in water, we'll get the corresponding nitro 2 and this aldehyde. Okay, so this was our target in retrosynthetic analysis in last slide. So now in this slide we see how we can plan, we can carry out the reactions to get this TGR product. Okay, so I guess you have get an idea about NAF reactions or Ampulang chemistry. Okay, so the next slide. So and this compound is equivalent to this compound. Okay, so in next slide we'll see the retrosynthetic analysis for this compound. Okay, now if we plan the retrosynthetic analysis for this compound, so this is having, so this is yeah, this is having this alpha beta unsaturated carbonyl compound as well as gamma methoxy. Okay, so this is the alpha, this is the beta carbon, and this is the gamma carbon. So where are the substituents? So in at gamma carbon we have this O methoxy, and alpha beta is having double bond unsaturation and this carbonyl compound. Okay, so we'll plan the retrosynthetic analysis or forward synthesis from this alpha beta unsaturated cyclohexenone. Okay, so this is basically cyclohexenone. So how we can plan, yeah, we will see in forward synthesis. Yeah, just a minute. Yeah. So from for forward synthesis, so we are planning the retrosynthesis for this compound, right? And the target material already we gave here. So this is cyclohexenone. So in forward synthesis, so we'll start from the cyclohexenone. So cyclohexenone we have taken. Now the next is we can add the lithiated pieces. So this 1,3 diethane derivative. Okay, so basically ampulang chemistry. Okay, so this is basically uh, acetaldehyde, right? So acetaldehyde, so how we can generate this acetal, the corresponding lithiated species of this acetaldehyde? So we can generate from uh, this 1,3 diethane species, and already we know the pK value of this proton is 31. Already we have I have shown you. Okay, so pK value is 31 now. So we have to take a stronger base, so which is having pK value more than 31. Okay, so we can think about this n-butyl lithium which is having pK 50. Okay, now I guess you have heard about secondary butyl lithium. Okay, secondary butyl lithium, I will show the pK value for secondary butyl lithium, also tertiary butyl lithium. Okay, so oh, which one will be the more stronger base? Okay, so you can think in your mind. So in between n-butyl lithium, secondary butyl lithium, and tertiary butyl lithium, which one will be the most stronger base? Can you guess? Okay, no problem. The pK value of n-butyl lithium is 50. I'll mention the pK value of secondary butyl lithium, that is 51. Okay, and tertiary butyl lithium, that is 53. 53, the corresponding pK value of secondary butyl lithium and tertiary butyl lithium. So by seeing this pK value, you can clearly think that tertiary butyl lithium is more strong base than secondary butyl lithium than n butyl lithium. Okay, now here n butyl lithium is okay, because to handle secondary butyl lithium and tertiary butyl lithium is quite challenging. Okay, those are more stronger base, so in presence of moisture it can create like explosive kind of things. Okay, so first we can generate this lithiated species from this 1,3 diethane by treating with this with n-butyl lithium, right? And we can get this lithiated pieces. Now this lithiated pieces basically this this C minus, right? So this C minus will attack now. Now if you see, it is having two electrophilic centers. So this cyclohexenone is having two electrophilic centers, right? So first one is this 1 2, and second one is this 1 2 3 4 4. So this center as well as this beta carbon, okay, both are electrophilic center. So now you are adding this nucleophile into this molecule, so what will happen? Two possibilities are there. It can attack at here, or it can attack at here. Okay, so now if you use simply this lithiated pieces, so basically this 1 2 addition will happen, so this reaction will not happen. And when this reaction will happen, if you add HMPA, hexamethyl phosphoramide, okay, HMPA is a highly polar aprotic solvent. So I will tell you the role of HMPA in next slide. Okay, so when 1 4 addition will happen, so 1 4 addition will happen when you will use HMPA, but without HMPA, normal 1 2 addition reaction will happen. Okay, so first basically in this case you will get this 1 2 addition, right? So this is the case 1 2 addition you will get. Now the next thing is that you have to do, uh, yeah, you have to do the protection deprotection of this uh, 1 3 diethane. Okay, so how you can do, you can easily do by using this silver chloride, sorry, mercuric chloride, right? HgCl2 in water and methanol. So what will happen, you will get this corresponding carbonyl group here. Okay, so this group will deprotect and you will get the corresponding ketone. Okay, so you'll get ketone. Now this interesting thing is that you are using methanol in your reaction and you are having the allylic alcohol. Okay, so this is the allylic alcohol. So what will happen, so Hg2 plus is there in your reaction medium. So this Hg2 plus will bind with this alcohol, allylic alcohol, and also this carbonyl ketone. Okay, so it will bind, so and it will make, so this is the 3-degree alcohol, so it can easily break this CO bond. Okay, so basically what will happen, the methanolysis of tertiary allylic alcohol. Okay, methanolysis of tertiary allylic alcohol, so basically this methanol will attack to this olefin in allylic position, sorry, to this olefin in vinylic position, and this CC double bond will migrate here, and this OH group C oxygen bond will disconnect and this alcohol will remove. So what you will get basically, so basically you will get this OMe at this center and double bond at this in between this CC. Okay, so basically you will get the product. So this is very interesting. So if you have this type of scenario in your molecule where you are having this tertiary allylic alcohol, also this alpha hydroxyketone, so in this condition easily you can do the methanolysis. uh, okay, so this is our target molecule. So you can see how we can synthesize this molecule from this cyclohexenone. Okay, now in next slide I will explain the role of this HMPA. Yeah, the role of HMPA, and so what is the yeah, what is the role behind 1 4 addition when you use HMPA. Okay, so I will see this 1 2 versus 1 4 addition role of HMPA. So basically this 1 3 diethane compound, so which is having pK 31, and if you want to deprotonate this CH, so you have to use this NBT lithium which is having pK of 50. Now, after having this lithiated pieces, basically this is C minus Li plus. Okay, C minus Li plus. So this is the compound. Okay, so C Li bond. So this is ionic. Okay, not covalent bond. Sometimes many people used to write this C covalent bond between C and lithium. So that is wrong actually. So you can better to write this C minus and Li plus because this is ionic. Now, when you are having this lithiated pieces, okay, lithiated carboanion. So, and if you treat this compound with this methyl vinyl ketone, so this is methyl and vinyl ketone. Okay, so methyl vinyl ketone is having two electrophilic center. This carbon and this carbon. Okay, now if you add this methyl vinyl ketone onto this compound, first in this first step, 1 2 addition will happen. Okay, now if you use, interestingly, if you use HMPA, what is happening, the reactivity is changing now. So now in this condition it will add to the beta carbon. Okay, so basically 1 for addition. So very interesting. Okay, so in first case without using HMPA, we are getting this 1 2 addition product. So the tertiary alcohol, and when you are adding HMPA, you are getting this 1 for addition. So what is the chemistry behind this HMPA? HMPA is nothing but it is a hexamethyl phosphoramide. Okay, so this methyl, this p double one o, nme2 nme2 nme2, so this is sp3. Okay, this phosphorus center is, if you want to know the hybridization, so this is the sp3 hybridized. Okay, so the what is HMPA? So HMPA is a polar, highly polar, so it is in polar solvent. It used to use as a solvent, and it is a highly polar, also it is aprotic solvent. Okay, so this is the character of HMPA. Now what is the role of this HMPA for this one for addition? So basically what will happen, so if you see this C minus and Li plus, so this is an so this is the uh, corresponding carboanion, and this lithium plus is the corresponding counter cation, okay, of this anion. So if you have strong, if you don't separate this cation and anion, then normally this 1 2 addition will happen. Now if you separate this carboanion and lithium plus, this plus and minus, this cation and anion, if you separate, okay, then what will happen, this carbanion will acts as a, so the nucleophilicity of this carbanion will enhance, okay, increase. So that time it will undergo 1 for addition. Okay, so how you can separate this C minus and Li plus? So there are mm, many solvents or many coordinating agents, so like HMPA. How, what will happen, so this HMPA, so this is the HMPA, so it will coordinate lithium plus basically. So by coordinating this lithium plus, it is making this carbanion free. Okay, so that's why the nucleophilicity of carbanion become more. Okay, so it can easily as a adds at the beta carbon. Okay, so this is the role of HMPA in 1,4 addition reaction for this 1,3 diethyne case. Okay, so I guess you have get idea what is the role of HMPA. Also there are many reagents like DMPU. Okay, DM, so similar kind of compounds, DMPU. So sometimes people use DMPU. Also sometimes people use TM, tetramethyl ethylene diamine. So the role is same. Okay, so compounds are different or reagents are different, but the role behind this is same. Okay, so both DMPU, TMEDA or HMPA, it will basically solvates the cation. Okay, lithium plus, and by solvating this lithium plus, it is making the nucleophile stronger. Okay, so that is the main scene for this type of case. Yeah, now so I guess you get an good idea of about using this HMPA in on for addition chemistry. So this next, if you see, this is the molecule. So it is in pyrocyclic molecule having this alpha beta unsaturated ketone in the 5-member ring chain. Okay, and this so how we can think about the retrosynthetic analysis for this molecule. Okay, so we can think about the so this alpha beta unsaturated carbonyl compound mean, we can think about aldol reaction, right? So aldol reaction mean beta hydroxy ketone. Okay, so from beta hydroxy ketone, so this is the beta hydroxy ketone. If we eliminate this alcohol, we can get this our desired target molecule. Okay, now, so from where we can get this beta hydroxy alcohol? So we have to think about aldol reaction. Okay, so aldol reaction between this so that will leads to the this CC bond disconnection. Okay, this CC bond disconnection we can think. So you see this and this will leads to the this carbonyl ketone and this aldehyde. Okay, so this one for dicarbonyl compound. Okay, so 1 2 3 4, so 1 4 dicarbonyl compound that leads to this compound. Now from where we can get this in 1 4 dicarbonyl compound? So basically, we can think about this CC1 disconnection, and that will leads to the this acceptor syntone, where this positive charge lies in beta carbon, okay, next to the beta carbon, next to this carbonyl, okay. So this alpha carbon and this is a beta carbon, okay, and beta positive charge, and this is the donor syntone, this acylium anion. And so these syntones we go get, so from here we can get the synthetic equivalents, okay. So basically for acceptor syntone, that will be the corresponding alpha beta unsaturated carbonyl compound. So, and for donor syntone, this will be the methyl nitromethane, okay. So nitromethane we can do NEF reaction, and we can easily convert this methyl to aldehyde, right? So that is fantastic. And this for this acceptor syntone, as I told you, so this will be the corresponding alpha beta unsaturated carbonyl compound, right? Yeah. And this we can get from, so if you can see this is an olefin, and we can think about Wittig reaction, okay. And Wittig reaction between the cyclohexanone and this Wittig ylide. So in so this Wittig ylide is commercially available, so if you treat these two components, and we can easily get the corresponding Wittig product. So this is the synthetic retrosynthetic analysis. So for forward synthesis, we'll start from the cyclohexanone. Yeah. So first, the cyclohexanone. If we treat about with this we take elide mean, so this PPSC plus and this C minus. Okay. So this elide already it's available. Okay. And if we heat or if we stir in RT room temperature in DCM, or if we reflux sometimes need to reflux if reaction is not slow, that time we can do reflux. So depending upon the substrate, we can do the heating or room temperature stirring, and we can easily get this we take product, okay. So after getting, and from here we can get this we take elide, as as you can see that we can take this alpha chloroacetone, okay. So this is the chloroacetone, acetone, you know, and this is the chloro substituted acetone, so alpha chloroacetone or chloroacetone. And if you treat this chloroacetone with PPH3 in toluene is solvent and room temperature. If you performing this reaction, so what will happen, this will SN2 will take place, or substitution nucleophilic bimolecular reaction will take place, and that will leads to this Wittig salt, okay. So PPHC plus, and what will be the corresponding counter anion, that is chloride ion, okay. So this is the Wittig salt you get. So after that, if we take this proton, so this is alpha acidic proton, uh, also it is next to the PPSC plus, so this is more acidic proton compared to this CH3, okay. So if you treat with this aqueous base sodium hydroxide in DCM in situ, you will get this anion, you can easily generated this carbo anion, and you will get this we take elide, okay. So we take elide, you can get, so and this we take elide, after getting we take elide, if you treat this with this carbonyl compound, you can get this alpha beta unsaturated compound, okay. So this is very simple. So next step is basically you have to add this nitromethane Michael addition, okay, a Michael addition or 1,4 addition of this nitromethane. So basically we you need dbu, so that will act as a base, and it will abstract proton from this nitromethane, and it will add to the 1,4 fashion to this alpha beta unsaturated carbonyl compound, okay. And it will give this corresponding compound. Yeah. So now if we do NAP reaction, okay, NAP reaction, there are many conditions for to convert this nitro to aldehyde. So like TiCl3 we can use the reductive condition where we can get this aldehyde, okay. So another way also we can get this aldehyde, so I'll show you. So we can add like we can have this compound. So these two compounds are similar, right? So, and then if we add this vinyl magnesium bromide, so this Grignard reagent in presence of copper iodide, so copper iodide, that means it will make this Grignard reagent soft nucleophile, and it will add to the 1,4 fashion. Okay, instead of 1,2 fashion, it will add to the 1,4 fashion in presence of copper iodide. Okay, copper salt. So you'll get this vinyl group. Now if you do this oxidative, this Lemux Johnson oxidation, okay, first diol formation followed by diol cleavage, oxidative cleavage of this diol, corresponding diol, we can easily get this aldehyde. Okay, so from two way we can get these two compounds, right? Very simple. So this, and this name reaction for this olefin to aldehyde, direct aldehyde, is known as Lemux Johnson oxidation. Many times I have told. And then if we do the sodium hydroxide mediated aldol reaction, so first we will get beta hydroxy alcohol, and then the elimination that will leads to the corresponding our dz target molecule, right? This is pretty cool. Yeah, so just wait for a minute. Yeah, so this example is done. So the next example is, yeah, this is also an interesting compound. If you see, so this is having, in this compound we are having this carbonyl compound, carbonyl ketone, and this alkyne, that is internal alkyne. And if you check the position of alkyne next to carbonyl, so that will be like here I have written already: alpha, this is beta, then gamma, delta, and epsilon. Okay, so this delta, epsilon, triple bond alkyne next to this carbonyl group. Okay, so from here we can get, so there is famous reaction of functional group interconversion known as Essen Moser fragmentation. Okay, so already I have mentioned here Essen Moser fragmentation. So that means if you have epoxide like cyclohexene, from here like this epoxide, then if you do the Essen Moser fragmentation, you will get automatically this delta epsilon alkyne. Okay, and from here you get this epoxide. Basically, if you have olefin here, and if you do oxidative, nucleophilic, if you treat this with nucleophilic epoxidizing agent, then you will get this epoxide. Okay, so nucleophilic epoxidizing agent mean you have to use sodium hydroxide. So normal MCPBA, it will not work in this condition because this double bond is electron deficient. Okay, NaOH and H2O2. So this is the nucleophilic epoxidizing agent. So it will generate in situ OOH minus. Okay, so OOH minus. So this will be the nucleophilic epoxidizing agent. So it will adds to this beta carbon, then this inolatoin form, and then elimination of this hydroxide ion will leads to this epoxide. Okay, so this alpha beta epoxy ketone already formed here. So now if you treat with this epoxy compound with tosyl hydrazone, sorry, tosyl hydrazine, it will form tosyl hydrazone. And if you treat this compound with base, okay, what will happen, this NH proton will take, base will take this NH proton. And if you see the arrow push mechanism, so this minus will fall here between N and N single bond, and this N C double bond will migrate, one bond will migrate to this position, and this epoxide ring will open, okay. So you will get this intermediate, and this intermediate, what will happen again, this O minus will fall back, and this CC bond will break, and it will leads to the triple bond formation between this CC bond, and that will leads to the elimination of this nitrogen and tosyl anion, okay. So basically you will get this alpha, beta, gamma, delta, epsilon, alkyne, okay. So this is very interesting, alpha, beta, gamma delta, unsaturated alkyne, okay. So if you need that, you can easily get from this compound, okay. And if you need delta epsilon, like normal double one, okay, instead of alkyne you need double one, what will happen, so that time you can just completely the same pathway you can follow. And if you do the reduction, like linear reduction, partial reduction of alkyne, you can easily get this alkene here. And that is not the mm, tough job, okay, that is easy to do, right? So this is the example, one of the good example. Yeah. So this is the next example, and this retrosynthetic analysis, if you see again, it is having this 665 ring, where one of the six member ring is aromatic ring, okay. So and this 6 5 fuse ring, and this having this alpha beta unsaturated carbonyl, alpha beta unsaturated ketone, okay. So you can think about aldol reaction, okay. This CC1 disconnection, okay, aldol reaction bit. So that will leads to this carbonyl and this carbonyl. So basically aldol reaction we can think, and we can easily carry out aldol reaction, right? So we'll get this two carbonyl compound on for diketone. So now this on for diketone, how we can get, so we can easily get from the reduced product like this alcohol product. If we do oxidation, we can get this carbonyl compound. Now from where we can get this, we can think about this CC1 disconnection, and we can think about this will be the delta positive and this will be the delta negative. That means this type of Grignard reagent we can plan, and this aldehyde is electrophilic, so this Grignard reagent will add to this aldehyde, um, which is more reactive than the corresponding ketone. So you will get this corresponding alcohol compound, okay. And how we'll get this, we'll get from this olefin via Johnson Lemux oxidation or ozonolysis kind of things. And from where we can get, if we do this CC1 disconnection, so we'll get this carbonyl compound and this allyl bromide, okay. So this will be our starting materials, and this is our target molecule, okay. Interesting. So what will be the forward synthesis? So if you see this forward synthesis, yeah, so we have to use some, we have this carbonyl compound ketone, and we are using LDA. LDA is lithium diisopropyl amide, right? So so this is a diisopropyl, So and we are having lithium plus and N minus. Okay, so this is the amide. Okay, corresponding amide, lithium diisopropyl amide. So the LDA. So if it is bulky base, so it will abstract proton here and it will generate corresponding enolate. Okay, so O minus Li plus. And if we add electrophile allyl bromide, we will easily get this CC bond formation product. Okay. Yeah. So after that, if we can do ozorolysis to get this carbonyl compound, or we can do this, already we have discussed about this Lemons Johnson oxidation to get this aldehyde. And then if we treat this aldehyde with isopropyls, not isopropyl, so this will be the isobutyl magnesium Grignard reagent. So it will add to this aldehyde and it will give this alcohol. Okay, secondary alcohol. So this secondary alcohol, further we need to do the oxidation of this alcohol. So we will get this 1 2 3 4 1 4 diketone compound. And if we do the annual reaction, okay, that means if we treat with sodium hydroxide, aqueous sodium hydroxide in ethanol under reflux, we will get the corresponding beta hydroxy ketone first, then we will get the eliminated product, okay, alpha beta unsaturated ketone, right? Yeah. So this is the example. So now coming to the next example. So this is the compound having this gamma lectone and the allyl side chain at this beta position. So how we will get? We can easily get, like, starting metal is already there. So this THP derivative. So this is the starting metal there. Okay. So how we can think about the forward synthesis? So if you this starting metal is carbonyl group is this side and the target molecule carbonyl group is the top phase. Okay. So how you can get? So we can think some functional group interconversions. Like first we can do the LH4 reduction. Okay, to for this ester to get the diol. Okay, so first we'll get this diol. Okay, and if we do the this is deep protection. Okay, OTHP tetrahydrofuran. Okay, so this THP group deep protection of alcohol under some mild acidic condition will get this triol. Okay, this triol, and among them this is the 1,2 diol. Okay, and we can easily think about oxidative cleavage of this 1,2 diol, and we will get the corresponding aldehyde, right? So aldehyde, and this aldehyde, if you see this alcohol, the position of this alcohol from this aldehyde, that is 1 2 3 4 5. So it will easily exist in lactol form. Okay, it will not exist in this form. Mostly it will exist in this lactol form. Okay, so now the job is easy. We need to do this lactol oxidation to get the corresponding our target molecule. So you can easily get this our desired target molecule. Okay, so this Jones oxidation we can carry out, and we will get this product. Very simple, right? Yeah. So you can see how easily we can convert the starting material where carbonyl group is from bottom phase, and we are converting this up. We are doing such a reaction so that this carbonyl group we are getting in a top phase. Okay, so this is the beauty of chemistry. And next example, so this is the retrosynthetic. This we can do the retrosynthetic analysis. So this is the target molecule. Okay, and this we could get from this 1 2 3 profile bromide. Okay, so basically this CC1 disconnection. Okay, so both side it is same 1 2 3 1 2 3. So this propyl bromide, and what is the other, and we can think about epoxide, right? So this propyl bromide is already there. So now this in this retrosynthetic plan, another like in this retrosynthetic plan, so what will be the other starting material, this epoxide, right? Now in another plan approach, we can think about this CC1 disconnection. Okay, so that means that will leads to this donor syntone and this acceptor syntone, right? So this is the donor syntone here, and this is the acceptor syntone for this retrosynthetic approach. So now what will be the synthetic equivalent? So this for this it will be the formaldehyde synthetic equivalent, and for this if you check it will be the corresponding Grignard reagent. So alkyl anion mean generally alkyl lithium or alkyl Grignard reagent we can think about. Okay, so this is Grignard reagent. Now this we can get from this corresponding alkyl halide compound. So this will be the synthetic equivalent. And from where we can get this? We can easily get from this alcohol, right? So this is the primary alcohol, sorry, tertiary alcohol, and this alcohol, if we like this alcohol to bromide, we can easily convert. And this alcohol, how we can get? So we can get like this CC1 again, this CC1 disconnection. Okay, so like this two, so this synthone and this synthone are same, and this is the acceptor synthone. Okay, donor synthone, two equivalent of donor synthone and one equivalent of acceptor synthone. Okay, so what will be the synthetic equivalent? So this is the Grignard reagent, butyl magnesium bromide, sorry, propyl magnesium bromide, and this we can get from this propyl bromide. Okay, and for this we can think about this methyl ester. Okay, acetate, methyl acetate will be the another starting material, right? Yeah, so we'll see the forward synthesis also. So forward synthesis we will start from this methyl propyl bromide and this methyl ester. Yeah, methyl acetate. So first methyl acetate, if we treat this two equivalent of propyl Grignard reagent, we'll get the addition of propyl group to this ester, and we'll get this tertiary alcohol, right? And this tertiary alcohol, if we can easily convert to corresponding bromide compound, bromo compound, by treating with PBr3. Okay, PBr3, and we will get this alkyl bromide compound. Now we need to convert this to Grignard reagent. Okay, so we can treat with magnesium turnings in presence of catalytic amount of iodine in diethyl ether. Okay, you will get this product. That product, this is the reagent. Okay, so now we need some other reagent that is called formaldehyde. So this will be the acceptor synthetic equivalent for acceptor synthone. Okay, and it will adds to this formaldehyde, and it will give this primary alcohol. Okay, so this is our TCR target molecule, right? Yeah. So coming to the next problem. So this is also having this cyclopentane of kind of ring and having this tertiary alcohol. Okay, so this retrosynthetic plan we can about think about this CC1 disconnection, and we can plan about this syntones, acceptor synton, and this donor synton. So this is the synthetic equivalent for acceptor synton, and this will be the region for this donor synton. Okay, so this Grenier reagent. Now this Grenier reagent, how we can prepare? So this we can get from this corresponding bromo compound. Again, this bromo compound we can get from this alcohol. Okay, already we have seen in last slides, last example. Now this alcohol, how we can get? So we can think about this CC1 disconnection that will lead to this acceptor syntone, and this is the synthetic equivalent. So this will be the highest corresponding epoxide. And the Grenier reagent. So this will be the Grenier reagent. So that will lead to the corresponding bromo compound. So that will be a synthetic equivalent for this Grenier reagent. Okay, and this also we can get from corresponding alcohol. Okay, yeah. In forward synthesis, we will start from this, and we can easily get this Grignard reagent. And then if we add this epoxide, we will get this alcohol, right? So now we need to convert this alcohol to bromide. So for that, PBR3 in DMF, we will get this alcohol to bromide. Okay. Now we will again convert to this Grignard reagent by treating the same condition magnesium iodine in diethyl ether. We'll get this Grignard reagent. Now we need the electrophile, that is the cyclopentanone. Okay, right? So the cyclopentanone is now we got. So this Grignard reagent will add to the cyclopentanone, and it will give the tertiary alcohol. Okay. Yeah, it will lead to the tertiary alcohol. So this, I guess, this is our this our DGR product, DGR starting material. Sorry, DGR target molecule. Yeah. So this is our DGR target molecule, and we convert our starting material to DGR target molecule. So we'll stop today. So again, we'll discuss in next. I guess last Friday I did not take the NPTEL tutorial. So instead of last Friday, I will have tutorial session on the coming Sunday. So please join on coming Sunday, and we will discuss other examples. So thank you for joining, and we'll stop today. And all the best. Yeah, thank you. We will stop today. Yeah.